Hi everyone, this is Maths for Uni. This is the worked solution to question 9 from the worksheet for lecture 4. If you find this content helpful, then please consider liking and subscribing, as well as checking out our Udemy course, of which the link is in the description. The question says, suppose that f of g of x is injective. Prove that g of x is necessarily injective as well. Prove by counterexample that f of x need not be injective. So let's break down what we have that we can assume. We have that f of g of x is injective. So if f of g of x equals f of g of y, then this implies that x equals y by the definition of injectivity. We want to first show that g of x is itself injective. So if you're unsure on how to proceed, then we should remind ourselves of what we want to show that g of x is injective. We want to show that g of x equals g of y implies that x equals y. So in order to prove this, let's start with g of x equals g of y. The only thing that we can possibly use is the result that we get from f of g of x being injective, which we have up here. In order to use this result, we can apply f to both sides of this here. And if we do that, we get f of g of x equals f of g of y. We've just applied the function f to both sides of an equality, and this gives us this new equality. But then we can use the injectivity of f composed with g, which gives us that x must be equal to y. Therefore, with one extra step, essentially we've shown that if g of x equals g of y, then x equals y. And we've done this by applying f and therefore going to f composed with g, which we had a condition for. Therefore, indeed, we have shown that g of x is injective. Now, despite being able to show this for g of x, we want to give an example where f of g of x is injective, but f of x is not injective. Let's pick an example of a non-injective function. Let's pick f of x to be x squared over the entirety of the real numbers r. We know that this is non-injective because, for example, f of 1 is the same thing as f of minus 1, even though 1 and minus 1 are distinct real numbers. 1 squared is 1, and minus 1 squared is also 1. So this will be our non-injective f of x, but then we want f of g of x to be injective as a composition. We know that h of x, with a new variable h, is equal to x, is injective. And so, if we pick the function inside the f, which is g of x, to be the square root of x, then what will we get for f of g of x? F of g of x is the square root of x for g of x, but then we square the whole thing by applying f. This is equal to x, which, as we above discussed for h, is injective. This may seem a little strange what we've done, but we've just said we know an example of a non-injective function and an example of an injective function, and then we've picked an appropriate g of x, which is the square root of x, so that the overall result, f composed with g, gives us this injective function that we picked up here, h of x equals x. Now, to ensure that this result definitely works as intended, we should be clear about the domain and ranges of our functions. So, in particular, for the sets that are involved, we have g going from r greater than or equal to 0, so that's the real numbers with 0 and all the rest of them that are positive. Also going to the range r greater than or equal to 0, and this is the function that takes x and outputs the square root of x. Again, we need the real numbers that are positive or 0 because we are going to square root them. And when we do this, we end up with another number that is either 0 or positive. Similarly for f, this is a function that takes any real number and spits out a positive or 0 real number. This takes x and goes to x squared. The overall composition, f composed with g, which we called h above, is a function from the positive or 0 real numbers to the positive or 0 real numbers that takes x and returns x back, i.e. the identity function. If you found this content helpful, then please consider liking and subscribing, as well as checking out our Udemy course. The link is in the description. Thanks for watching, and goodbye for now.